For the Sofia pendulum experiment, we brought a pendulum and a device called a photogate that can measure the period of a pendulum very accurately. We hooked the photogate to a computer so we could measure a bunch of periods for our analysis, and we were curious what would happen to the period of a pendulum if we measured it on the ground compared to up at 43,000 feet in the stratosphere. And so what do you think is going to happen? Will flying in the stratosphere make the period, well, is it going to be the same? Is it going to be greater than on the ground or less than on the ground? And think of your prediction. Pause if you need to. Here comes the answer. And it should be greater than on the ground. In other words, a longer period, the pendulum is going slower. So why would that be the case? Why will the period be greater in the stratosphere? Think about it. There's a few choices there. Pause and think about it. Here comes the answer. And it's because Earth's gravity is weaker. Now, you might have picked A, but the key thing in A is it says the mass of the pendulum. Mass doesn't change depending on your location. So the mass of the pendulum is the same on the stratosphere as it is on the ground, or even if I took it in the moon, to the moon. What would change would be the weight. And so if I said the weight of the pendulum is less, then A would be correct. Weight and mass are not the same thing. It's true that the air is thinner, but again, we're in Sofia, so that's not really going to matter for a simple pendulum. The amplitude doesn't affect the period, and we are assuming this is a simple pendulum. And so Earth's gravity gets weaker as you move away, and that causes the pendulum to go slower because gravity is the restoring force and there's less of it. So here's our experiment and our data. So this is on the runway. We're at an elevation of 773 meters. That's the elevation of the ground above sea level. And so our altitude is 0. And we have a latitude and a longitude, which could be important for our analysis. It turns out especially the latitude is. And here we are in the stratosphere measuring it. And the elevation of the ground below us is 1,144 meters, and then 43,000 feet corresponds to 13,112 meters. And so when we're trying to figure out what we expect to happen, we want to be able to calculate how strong gravity is, and knowing the altitude and elevation will help us do that. And again, the latitude and longitude are given. And fortunately, the latitude is very similar, which makes our analysis a little easier. And so this is the raw data. The first run, you might notice it says run number 2. And so the first run, we were just adjusting things. And so we would move the photogates and adjust the pendulum and things until it was settled. And so that data was not useful. And so run 2, everything was set and we didn't change anything. We started the pendulum going. But when you do that, it's really hard to let go of the pendulum and not have it shake a little bit. And so we're neglecting the first 5 periods. The pendulum shaking was not noticeable after about 3 periods. But to be safe, we said 5. And we should use all the data, but the run on the ground, we collected 11 data points after the first 5, and then we collected more in the stratosphere. So we're just going to say, let's just pick the first 10 just because 10 is easier. Maybe we should have done 11. Not a big deal, though. And so if we average the data together, you can see the mean for the ground is 2.158. And I'm just going to take the first 3 digits here. And then the average for the stratosphere is 2.163. And so the period is greater in the stratosphere, not by very much, and maybe our data is noisy and we can't even make a conclusion here. We'll talk a little bit about that, but it definitely is a longer period in the stratosphere. And the ratio of those 2 periods, the ratio demonstrates how close the periods are to each other. And so let's see if we can figure out what the expected ratio is. And so the period of a pendulum is given by 2 pi square root of L over G. And if I write it as a ratio, then I don't need to know the length of the pendulum because it's the same pendulum used in both experiments. This is period in the stratosphere, period on the ground. And then also the rest of our calculations simplify. The 2 pi divides out. And then if I divide square root of 1 over g stratosphere by square root of 1 over g ground, it simplifies to this. So all I need to know is what is the gravitational field strength on the ground, on the runway, and what is it in the stratosphere. And Newton gave us an equation for that. It's the gravitational constant g, big G, times the mass of the Earth, divided by the distance from the pendulum to the center of the Earth. And so big G I just looked up. I'm only showing the units for the answer. If you want to be a stickler for units, you can look that up. But it's Newton meter squared over kilogram squared is one way to write it. And this is the mass of the Earth in kilograms. And then the distance to the center is the radius of the Earth, sea level, plus at that latitude, plus our elevation. And it turns out this is pretty insignificant, but I added it anyway, and I get 9.817 newtons per kilogram for the gravitational field strength on the runway at Palmdale. And then G in the stratosphere, little g, is big G times the mass of the Earth, so same numbers as up here. And then R, it turns out since we're at the same latitude, the radius of the Earth, the distance to the center of the Earth is the same. The distance to the center of the Earth is greater if you're at the equator than at the poles. And so this could be different depending on our latitude, but it turned out we were fortunately at about the same latitude. And then this is the sum of our altitude and the elevation of the ground beneath us. And so I added both of those numbers that were given previously together, and I get 9.776. And so the gravitational field strength of the Earth is a little bit less in the stratosphere. And so now if we put these in to little g, you get agreement with what our measurement was. But there might be something else going on here. And it turns out there is. If you have a pendulum in an elevator, while the elevator is accelerating, its period will be different. And it turns out the pendulum is accelerating, as is everything on a rotating Earth. And so this acceleration is downward, and it's given by this equation. And so what I want to do is solve for this acceleration and subtract it from little g and see what the expected ratio would be. And so this has a name. It's called centripetal acceleration, and v is the speed of the pendulum, and r is the distance to the Earth's rotation axis at this latitude. And so first we're figuring out r, little r. So here's the Earth's spin axis. It's rotating around that. And so here's the pendulum on the runway. And so this is the radius of the circle it's going in. It's kind of going around like this, just due to the Earth's rotation. And then this is big R. This is what we had on the previous page. Radius of the Earth plus our elevation of the site. And so little r is 5.245 times 10 to the 6 because it's, this is theta, and so it's adjacent. We have a right triangle here. And so figuring out little r, now we want to figure out the speed. And so the speed is the distance over the time. And so if the pendulum stayed on the ground for a day, it would go around in a circle, 2 pi r, where it's little r from up here. And then that would be the time it took one day, 24 hours times 3,600 seconds per hour. Again, I'm leaving the units out, but you can see in my answer what units I was using. And so this is how fast the pendulum is going and everything else sitting on the runway. And so the acceleration is very small, but again, we're looking at small differences, so maybe this will be significant. What about the acceleration when we're in the stratosphere? Is that very different? Well, it turns out it is based on how Sofia is flying. So first of all, we need little r just like before. And so it's big R times the cosine of the latitude, which was coincidentally the same as the runway. And then the speed is distance over time, but this is the speed of a point moving with the Earth. And so that's due to the speed of the Earth's rotation only. Sofia at this point was heading due west. And so its speed relative to the Earth's rotation axis is going to be less. Everything is moving east at this speed, and Sofia was heading the other way, and so I need to subtract that. And so Sofia's acceleration turns out to be a lot less due to this going in a circle around the Earth. And so the g that you use in the pendulum equation, which is not trivial to show this, is adjusted based on whether the acceleration is up or down. If the acceleration is up, like in an elevator speeding up on the way up, you feel heavier, you would add it to little g. But in this case, the acceleration is toward the center of the circle, and so it's subtracted, and so the g on the ground is a little bit less than what we got. It's not really little g, it's the little g we're using. It's g minus the acceleration. And then for the stratosphere, I subtract a much smaller number, so that didn't change as much. And so really the expected ratio is 1.001. And so it shows that our agreement isn't as great as we thought. And probably if you look at how accurate a photo gate is, we're borderline whether we even found a significant difference. But we enjoyed doing it and doing the analysis to figure it out. And I hope you enjoyed going through it with me.